Hello everybody, welcome to Akamoth Musings channel. This is a continuation of Playing with Fractions series of videos. In the previous video we introduced two addition operations. One is called dual of the other, but we have not introduced zeros or identity elements for those operations. And this will be the topic of today's video. In addition, I want to mention the notion of infinity, because many algebraic structures in classical mathematics has already described the role of identity elements, such as monoids, groups, fields, rings, algebras. They all have identity elements, but this is not the case for infinity. So infinity is somehow handled in a nice way in projective geometry, but that's a geometric perspective view. And in this video I want to cover algebraic perspective and how in our system that we built in the previous video, how infinities become zeros actually. So these entities, or zero and infinities, are pretty much the same entities but viewed from different perspectives. So let's move on and consider two operations that we introduced in previous video. Let me just jump to the next slide here. So in the previous video we had plus operation and we had plus operation with hat on the bottom, and we considered the physical interpretation of this operation. So if we have a circuit like serial connection of two resistors R1 and R2, then the total resistance R serial will be equal just R1 plus R2. For the right hand side, we found that we need to consider parallel connection in order to get the effect of this dual plus operation. So R parallel will be equal R1 plus with hat on the bottom R2. Let me just denote R1 here and R2 here. So I want to introduce two zeros for each of these operations. So 0 on the left I will denote with hat on top, and 0 on the right will be hat on the bottom. Let's just split this on two halves. So the zero element is expected to preserve the quantity it is added to. So I want an element so that I add it to, let's say if I add 0 to R1, I want still to get R1 as a result. On the right side, if I add 0 to R1, but that's different 0, I want to get R1. Okay, that's the property of 0. So now I want to see what's the physical interpretation for this 0. So for parallel connection, of course, if I just add a wire here or just no resistor, okay, then it will play the role of 0. But wire already have some resistance, so to be more close to abstraction of 0, I will just say that I have a superconductant element here, and that this is the 0, okay? So then the total in this case will be just equal to R1. On the left side, let's think a bit what can be the 0. So what we want is some element on the bottom. Just let me have a space here. So R1 is here on the top. On the bottom we want R2, some element here that will not change the resistance of this circuit. So if I think a bit, then just cutting the wire here, just cutting the wire, I will note it with a cross, will lead to a topology equivalent to something like R1. to this, and this will definitely have resistance R1. So the 0 is just a cut wire on the right side. From the other perspective, cut wire has infinite resistance. So we should interpret this as infinity. So 0 for this addition operation is equivalent to infinity, infinite resistance. So we mark it, we have this correspondence. So let's move on. We introduced these two elements. Now we want what we have. We have multiplication operation, we have addition standard, we have dual addition, and we have identity elements for them 1, and we have 0, and we have 0. So to make the system complete, we just need to take all these elements, apply to them all the operations, and define what is the result of those applications. But in this video I will focus just on a few cases, and the rest will be covered later. So let's figure out what is 0 multiplied by 0. We don't know this yet, but let's recall the duality principle. Have this property that if we have, for example, r that is equal r1 plus r2, then we can make a dual expression for this. It will be same as 1 over r equal 1 over r1 plus dual plus 1 over r2. That's the dual expression. So how it works for zeros? We want this to work for zeros as well. So for 0, we will get that r1 equal r1 plus 0. Its dual will look like 1 over r1 equal 1 over r1 plus, and here we have something like this. In order for this to work, because this is equal to this one, we need to interpret this as an identity element. So it's also 0, and this is, we know we have a 0 for this plus operation. It's denoted as this 0. So we see that in order for our duality to work nicely with zeros, we need to admit that 1 over 0 is dual of 0, and 1 over this 0 is dual of this 0. So from this we see that 0 multiplied by 0 is equal to 1. It is also visible here that we can, another notation for this will be infinity with hat on top, and another notation for this one will be infinity with hat on the bottom. So it will also look like if we multiply 0 on infinity, we get 1. And it is the same as if we multiply dual 0 on dual infinity. So these are just operations that we can introduce with both zeros, infinities. So zeros and infinities basically the same. One is dual of the other. Let's now look at how we sum these zeros. So we have a number of situations. Let's have sum here, and on the right side we have sum, dual sum. So we want to know what is 0 plus 0, and we want to know what is dual 0 plus dual 0. And at the end we want to have a mixed addition. Let's just do the same on the right side. We want to sum with another summing operation. Sorry, 0 here. Oh my god. 0 plus dual 0 and just regular 0 dual plus dual 0 equal. So in order to figure this out, we could use purely just abstract inference and just consider all the cases that are possible. But I will follow in this video our physical example of electrical circuits and figure it out that way. So let me just, for the first equation here, 1, let's say 2 and 3, let's like give it a name. So for the first one, we have superconductance. So just remember, this is a serial connection, and this is parallel. So for the first one, we have two superconductance elements connected in a serial way. Clearly, the result will be just superconducting element. For the second case, physical interpretation will be two cut wires connected in a serial way. And of course it will be a cut wire. And third is when we have a superconductance and a cut wire. Then the result will be a cut wire. Okay, let's move on to the right side. Two superconducting elements connected in parallel. We can show it like this. Of course, the result will be a superconducting element. For the second one, we have two cut wires connected in parallel. The result will be a cut wire. And third one, we have cut wire on one branch and superconductance on the other branch. We will get superconductance, which is noted like 0 with hat on top. So these are, let's consider these equations. What we can see here is that when we add similar elements like here or here, and on the right side here and here, we just get a preservation. So adding zeros lead to zeros, adding dual zeros lead to dual zeros. Same on the right and left side. But when we add two different zeros, we get a symmetric situation. So this one and this one look symmetric. Okay. Here we get dual zero, here we get just regular zero. And if we express this in terms of, let's say, just 0 and infinity symbol. So what we have here is 0 plus infinity, and we get infinity. Very nice expression, right? Totally understood. On the right side we get 0 plus infinity, but we will get 0. This looks weird, right? But we know that left and right side is completely equivalent. So train your abstract mind to perceive these two situations as all legitimate and equivalent. And if you don't want to do it alone, subscribe to my channel. I'm going to show you more examples like this. Thank you very much. It was Alexander on Akamath Musings channel. See you next time.